Hi there. We're going to take a look at the last few problems on test review number 3. So for problem number 29, we have the sum n going from 1 to infinity of n over negative 2 raised to the power n. So the first thing that I want you to notice about this problem is that we have an embedded alternating component. And so my first step will be to factor that out. So the remaining sequence part then is n over 2 to the power n. So this is definitely a ratio test type problem. We see that power tower, n is part of the base number and the exponent. So we set up the limit as n goes to infinity of a sub n plus 1 divided by a sub n. In this case, the limit as n goes to infinity of n plus 1 divided by 2 to the n plus 1, all over n over 2 to the n. So since we have a composite fraction, I'm going to flip and multiply that denominator. I'm also going to rearrange my terms just so that like terms are more or less together. And then we're going to start canceling. So when I cancel, the 2 to the n divided by 2 to the n plus 1 will simply be left with a 2 in the denominator. And as far as the n plus 1 over n terms, there's no simplification there. But taking a look at my cleaned up or simplified limit, so this is the limit as n goes to infinity of the absolute value of n plus 1 over 2n. This is a limit of a rational expression where the degree of the top is the same as the degree of the bottom. So this limit will go to the ratio of the leading coefficients, 1/2. And since this limit is less than 1, the original series will converge, and converge absolutely by the ratio test. For problem number 30, we have the sum as n goes from 1 to infinity of 6n squared plus 2 divided by 12 minus 2n squared quantity raised to the power n. So anytime my entire quantity is being raised to the power n, that's a telltale sign that this is going to be a root test problem. So I will set this up as the limit as n goes to infinity of the nth root of my expression 6n squared plus 2 over 12 minus 2n squared quantity to the power n. So the nth root and the power n are going to cancel each other out. So we have the limit as n goes to infinity of 6n squared plus 2 over 12 minus 2n squared. Again here, I'm finding a limit as infinity of a rational expression where the degree of the top is the same as the degree of the bottom. So this will go to 6 over negative 2, of which the absolute value is equal to 3. So by the root test, this series will diverge. Problem number 31, we're going to consider the infinite series negative 1 to the power n divided by n plus 2 factorial. Step 1 is to check and see whether this series will converge or diverge. And so for this, again, I'm going to just first factor out that alternating component, and I'm going to use the alternating series test. So I'm going to check, is 1 over n plus 2 factorial decreasing? And you can really quickly graph this. I can see term-wise this definitely is decreasing, so check. Property number 2, the limit as n goes to infinity of 1 over n plus 2 factorial is equal to 0. So since both two properties hold, we can conclude that this series will converge by the alternating series test. We may have been better off using the ratio test to check this series. The ratio test would, from the get-go, have tested to check and see if this convergence is absolute. But now we're left to check that whether this convergence is absolute or conditional. So if we take the alternating component away, I see that this series, if we use the ratio test here, the limit as n goes to infinity of 1 over n plus 3 factorial divided by 1 over n plus 2 factorial is going to be equal to the limit as n goes to infinity of n plus 2 factorial over n plus 3 factorial. I see here the limit as n goes to infinity is of 1 over n plus 3 is going to be equal to 0. So this thing does converge by the ratio test, and therefore I know that the original convergence is absolute. Again, it would have saved a step to use the ratio test from the get-go, but this is an alternative way of also doing it if you absolutely want to use that ratio test or that alternating series test. All right. So we would like to find the partial sum S sub 5. So this simply means we're going to add up the first 5 terms of this series. So negative 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial plus 1 over 6 factorial minus 1 over 7 factorial. When I sum this up, I get a value of negative 0.132142857. This problem wanted us to round to 5 decimal places, so make sure that you do round correctly. Alright, the next part of the problem wants me to use the alternating series estimation theorem to give an upper bound for the error in using the first 5 terms to estimate the true value of the series. So the alternating series estimation theorem says that R sub 5, or the remainder after 5 terms, which is the same thing as the true sum minus the partial sum S sub 5, will be bound by whatever the next element in the sequence was, in this case b sub 6. So b sub 6 for this problem is 1 over 6 plus 2 factorial, which is 1 over 8 factorial, and that's going to be equal to 0.0000248. Again, this problem wanted you to round to 7 decimal places, so that value right there is ready to go. Alright, in the next part of the problem, we want to find the smallest value of k so that the sum S sub k is guaranteed to be accurate within 0.00001. So this means that b sub k plus 1 needs to be less than that value. So we need to come up with what is the term b sub k plus 1 look like. So again, if we just substitute k plus 1 in for n, we're going to get 1 over k plus 3 factorial. And this is going to be less than 0.0001. I'm going to turn that decimal into a fraction because what this will allow me to do is, since I now have a fraction on both sides of this inequality, we can essentially flip both sides. Just remember that when you flip or reciprocate over an inequality, that the inequality sign will also flip. Alright, so now we're going to use basically a trial and error method to find out what k has to be. So I'm going to create a little list. I know that 7 factorial is equal to 5040. That's too small. 8 factorial is equal to 40,320. Again, we're not quite at 100,000. 9 factorial is equal to 362,880. That number works. So we know that k plus 3 must be equal to 9. And therefore, we can say that k is equal to 6. Alright, the last problem here, number 35, wants us to use the ratio test to determine the outcome of the sum of 2 raised to the power 3n plus 2 divided by n times 6 to the power n. So setting this up using the ratio test, the limit as n goes to infinity of a sub n plus 1 divided by a sub n, I'm going to get 2 raised to the power 3 times n plus 1 plus 2 over n plus 1 times 6 raised to the n plus 1. All of that divided by 2 raised to the 3n plus 2 divided by n times 6n. I'm going to flip and multiply, and as I do, I'm also going to clean up a few things. Be very careful when you distribute 3 times n plus 1 plus 2. Make sure that you distribute that 3 properly. So if distributed correctly, we're going to get 2 raised to the power 3n plus 5 divided by 2 raised to the power 3n plus 2. We also have 6 to the n over 6 to the n plus 1 times n over n plus 1. So as I flipped and multiplied, I also rearranged so that I would get like terms together. And this is going to allow me to clean up a little bit easier. Alright, so as far as the base 2 terms, there's 3 more in the numerator than there are in the denominator. So we're left with 2 cubed in the numerator. The base 6 terms, I have 1 more in the denominator than in the numerator. So we just have a 6 in the denominator after cancellation. And the n over n plus 1 terms will not simplify. So I'm just going to leave them alone. Alright, so this limit, if cleaned up, is going to be equal to the limit as n goes to infinity of 8n divided by 6 times n plus 1. Finally, we can simplify this to the limit as n goes to infinity of 4n over 3 times n plus 1. And so in part 2, The question is, does the series converge or diverge? Well, we see since this limit goes to a value of 4/3, 4/3 is greater than 1, this series will diverge by the ratio test.